All right, so last time we were talking about binary search trees, and we outlined each one of the basic operations. Search, where you start at the root, and then you either go left or right because of the binary search tree property. You only have to go left if the thing that you're searching for is less. You only have to go right if the thing that you're searching for is greater. And you go down until you go past a leaf where you find what you're looking for. And that's going to be a complexity of order D, where D is the depth of the tree, because of course you only have to go as deep as the tree exists. With insert, it's going to be almost exactly the same, but you start at the root and you traverse left or right until you either find the element, in which case you're going to reject it because it's a duplicate, or you're going to find where it should have belonged, and that's where you end up inserting it. You always end up inserting it as a leaf node. Right? Once again, this is going to be order D because it's just a search operation. And then finally, deleting. Right? Now, there are three different cases here, because if you delete a leaf, for example, then there's no problem. Right? You just go back to the parent and then you sever that relationship right there. If it ends up such that there's a left child, right, then what you would do, and the node here ends up being a right child, then all you need to do is promote that left child up. Right? In other words, if there's only one child, whichever child it is, left or right. There are going to be several sub-cases there to deal with. And then finally, what happens if you have two children, right? That means that you can't necessarily bring one or the other up, because there might be an entire tree hanging up over here, and there'd be 1, 2, 3 children, and that's not a binary search tree. It's not a binary tree at all. So what we decided was, well, go to the left subtree and then find the maximum value, 49, and then place that up here, 49. Right? Now the binary search tree property is preserved, but you of course have a duplicate 49 here that you have to get rid of, and therefore you have to delete one more node, the 49 that you just promoted up. And that's guaranteed to only have one child because it would not have been maximum, right? If there's two children here, then there would have been something that's right child that is greater than it. All right? So what we're going to do is we're going to spend the rest of our time implementing this over here in Java and executing each one of these operations. Now, my first choice is I could implement this by extending a binary tree. So let's go ahead and create a binary search tree, T, right? And what I could do is I could extend binary tree, because a binary search tree is a tree, right? It is a tree, but it's a binary tree. So I could have had like a binary tree, binary search tree in my inheritance, but that would be kind of like going all the way back to the beginning of the semester, where we had a person, a director, and an author, and sometimes they were both, right? Does that really make sense, right? It doesn't necessarily violate the Liskov substitution principle, but understand what we would end up inheriting from this. We would end up inheriting preorder traversal. Does that make any sense on a binary search tree? No. BFS traversal? That doesn't make any sense either, right? The iterator that does a preorder traversal? No. No. That we would end up inheriting something like, say, inorder traversal. Did we not do that? I guess we didn't do that. But did we talk about inorder traversal? I'm pretty sure we did. Right? An inorder traversal on a binary search tree would make sense, but we ended up not even implementing it apparently. Right? So I'm not going to do that. I'm just going to go ahead and have this as a standalone class. I'm not going to lock it into that hierarchy. Okay? So let's go ahead and create a private tree node, T, right? And that's going to be my root. And I'm also going to want to keep track of the size of the tree, so let's go ahead and create a size. Anytime I insert something, I'll increment that. Anytime I remove something, I'll decrement it. So let's go ahead and create a public binary search tree constructor here. This dot root will end up being null initially, and this dot size, well, if we don't have anything to start out with, it's going to be 0. Okay? Now let's design our interface first, and then we'll go ahead and go back and fill it in, just like we did with the list data structure. I need a way to put stuff in. So public void add an element of type T, right? And it adds X to this tree. I need a way to retrieve something. So public void search, because it's binary search tree, right? TX. And it's not going to be a void here. I'm actually going to return the element that you're asking for. Okay? And then finally, the CRUD, we're going to ignore update for now. Void, delete, or remove an element X. Okay? For now, I'm going to go ahead and return null here just so that it compiles, because I want to focus on this one first because that's the order that we did them in. The simplest one. In fact, once we've done this first one, that will give us basically most of what we need for the second one. Okay? All right, so, sorry, search is what I want, search, right? Yeah, search. Search is what we'll do first, okay? All right, so let me just go ahead and do the first iteration here, where I look at the root element and see if that's the thing I'm looking for. For example, over here, if I were searching for, say, 48, right? Search for 48, right? Then I would start at the root and see, is that the thing that I'm looking for? Right? So is whatever the element is in the root, is that what I'm looking for? This dot root dot get element, or get element, right? Is that equal to X? Right? If so, this is an if statement. If that's equal to X, I will return this dot root dot get element, right? Because I found what I'm looking for. And we'll come back and fill this in here in a second. Else if this dot root dot get element is less than X, or let's reverse that. I want to go left and then right. There we go. So if the thing I'm searching for X, in fact, if we want to, we can go ahead and rename this appropriately. What would I rename this? Not just X. I'm searching for a key, right? There we go. So if it's equal to the key, then you found it. Otherwise, if the key element is less than the root element, then I will go left. What's the only other possibility? It's greater, go right. I don't need an if statement there. Now let's come back and fill this in. How do I compare the element to the key? So equal to option 1. What does that do in Java? What does that do in most static programming languages? C, C++, Java.
The actual data value.
The memory address, right? And that's not what you want, because 10 and 10, I could have 50 different 10s and they're all in different memory locations, right? So I don't want that. Remember that we always have this dot equals method, right? That'll work, but will that tell me that it's less than or greater than? When I go down to see if I need to go left or right? No. So what do I need here? I need something to compare elements of type T. Right? What is that thing called? A comparator. Private comparator T. I'll just call it CMP for short. Right? Because that, if I give these two objects off to it, the current object and the key, it'll return something negative, positive, or 0 depending on the relative ordering of these things. So how do I use that? This .cmp compare the root element to the key element. Let me go ahead and switch those around so that it's consistent. Key and the root element there. And what will it return if they're equal? 0. Right? Otherwise, if I compare them and it returns something negative, right? Note here, this is why I switched them around. I'm going to preserve the order key, then element, and then less than 0. So the less than sign stays the same, right? So if you compare the key and the root element, and it gives you something negative, that means that they're in order, so you need to go left, okay? We'll worry about this here in a second. That's okay for the root element, but clearly I would end up going left here. At that point, I need to compare it to this element right here. Then it would go right, and then I need to compare it to that element right there. Each time, I would update the node that I'm currently standing on and examining. So I don't always want to do this with the root element. I need to keep track of the current node. So tree node, T, current. Where do I start? At the root. Right? Then while the current has not fallen off the edge of the tree, right? Then I will repeat this entire process here. Okay? Now I'm no longer comparing the root element, but I'm comparing the current element, right? And the current element. Right? There we go. Sometimes it helps to write the first iteration, right, of a loop, especially if it's a while loop here, and then generalize it. Okay, and that's what I just did here. So it has not fallen off the edge of the tree. How do I translate that to code? When it falls off the edge of the tree, say that I'm searching for 42 instead, right? I would go left, right, left, and I've fallen off the edge. What is the current node now? Null, right? That's our placeholder value for nothingness in Java. Right? So while the current node is not null, keep going, keep going, keep going. Now that I've got the current, I can actually go left. Current is equal to current dot get left child. Right? Current is equal to current dot get right child. Right? There. If you get down to the end here and you never find what you're looking for, you've broken out of this while loop because now the current node is null, right? Searching for 42, for example. Did you find it? No. So we will go ahead and return null. Right? Let's document it to understand, right? So searches for a value in this BST, a binary search tree, that matches the given key code key element, right? Returns code null if no such element. All right, I'm glad that I clarified that this was a key, because suppose that this was an integer, just a bunch of integers. You asked, find me 10 in this tree. I'm going to give you 10, and what are you going to end up returning? 10. Why did I ask that question before if I've got it in my hand giving you the key? Right? That's because generally here this is type T. Right? Remember way back at the beginning when we were searching through books for a book by a particular author. We couldn't take an author and then compare it to a bunch of books. We had to create a dummy book value. We called that a key, or now we call it a surrogate key, just like we do in databases, right? It is a key that matches the author. So we took the author, put it into this book. We didn't set the title. We didn't set the ISBN. That was our only search criteria, because we have to compare apples to apples and oranges to oranges. We can't compare authors to books. So we have to create this book key, right, in order to find the actual book value that corresponds to that key. And that's what we're returning. We would end up returning a book with the title and the ISBN and all that data actually present, just based on this partial data over here. Or in your project, I'm searching for an invoice. I can't just give it a UUID, right? I have to give it an invoice with the UUID set to the one that I'm searching for, and then it gives me the full invoice over here, right? Something like that. So this does make sense to give it a T and return a T, right? Because it's not the exact same T. It is, I'm glad that I brought that up. What should we be returning here? Just always the root element? No, not the key element, sorry, but the current element. Right? Once you find what you're looking for, that's the element that you want to return, not the original key, and not just the root. There's no way to test this, because I've not been able to get stuff into my tree yet. That is step 2. Let's go ahead and do the insert method now. Right? Add over here, okay? All right, well, we can search for it, find where it should be. So I'm gonna go ahead and steal this code down here, right? Because the first step is going to be to find it, right? And there is no key element. So here I will change it to X and X. All right, there you go. And why are you, oh, okay, yeah. All right, we'll come back to this here in a second. All right, but now think about this. When I'm searching for 42, current, let me go ahead and outline this over here. This will end up being current when I search for it, right? Am I going to be able to insert it right there? It doesn't exist, it's null, right? I have no information. What I actually need is its parent so I can set its left child to this thing, right? So we're kind of sunk. I can't do a search for the item if the item's not in there, so I have to do a search for the parent. In other words, I would have to change this loop here. Not while the current is null, but by looking ahead. The next element, if that's null, then stop, right? And that's where you want to stop. I want access to this 45 right here, the previous element. So you can go ahead and change this entire loop if you want to, or you can do what we did with a linked list, right? If we needed to insert something, we needed the previous one because we needed to go back and make that point to the new node and make this one point to that node and make that then point to the next node. So I'm going to keep track of two things: previous and current. That way I only have to do one search, right? So we'll come back to this over here, right? I'm going to update the previous to be current. Right? In other words, the previous now is the current, and then the current gets updated to the next, right? And I'll go ahead and just put this in both of those loops right there. Okay? The previous had to be done first because you're overriding the current on the next line right there. Okay? All right, great. At that point, I'm not going to return null here. What am I going to do? I now need to add the new node as the new child of current, ... Okay? In this particular case, I would add 42 as the new left child of the previous, right? But what if I were inserting, say, 99, right? I would come down over here, and I would end up inserting it as a left child. So I need to create the node, and then I need to determine, should it be a left child or the right child of the previous, right? So step one, create the node. And we've had experience doing this. Tree node T, new node is equal to new tree node holding the element X, because that's what we're inserting, right? Part two, I need to set new node's parent to current, or previous, excuse me, previous. Because of course current is null, and the new node is actually going to be the current when I'm done, right? Or conceptually, not exactly, but conceptually. So set the new node dot set parent to previous. Okay? And now I need to determine, is the new node the previous's left child or right child? Okay? And for that, I'm going to go ahead and steal this code up here, because that's exactly how we determine should we go left or right, right? All right, so if I compare, not the current, but the previous, and X is less than it, then it should be the left child. Right? So new what is it? Previous dot set left child to the new node. Right? Otherwise, it should be the set right child new node. Right? What else should I do? I've increased the size of the tree by 1, so this size plus plus. Right? Now it's still not compiling because of this error up here. Let's move that over so I can actually see the right side there. All right, that's because down here we cut and pasted this code for search, which returned the element. We don't really need to return anything up here since it's void. But do you remember we followed a couple of patterns already where, well, I don't want to waste that return value. I want to communicate something back to the calling function, even if the calling function doesn't want to listen to me. I want to communicate that, that it worked, or that it had an effect. We could change this to a Boolean value, right? Now, what does it make sense to return here? You already have the element in the tree. Insert 5, but 5 was already in the tree. Remember that we're not going to allow duplicates, at least for this run, right? For our purposes, the data and the key will be the same. We'll use integers, and we'll assume that they're all unique. Okay? So in other words, this is a duplicate. I could throw an exception, throw new exception. I don't like that, though, because generally what I want to do is I want to keep things moving along, right? Instead, what I'm going to do is, we called this a noop for no operation. Right? So I'm not going to do anything. I'm just simply going to return false. It did not have an effect on the tree. Right? So what this function does is it adds the given element, code X, to this binary search tree and returns true, and returns true if successful, or false code if the element is already present in the tree, right? And no operation, right? We're not going to end up actually changing the tree, right? That means down here, what do I need to return if I actually inserted something? True. Right there. Okay. We now have enough to test this. So let's come over here to demo, right? And I'm going to go ahead and get rid of all of this. And I'm going to create a new binary search tree just for integers, because that's easiest to look at, right? BST is equal to new binary search tree. There we go. Except for, wait a second. What about that comparator? Did we ever initialize it? Nope. So if you're going to create a binary search tree for T's, you need to give me a comparator for T's. In other words, you need to provide that as part of your instantiation. Right? Okay? What if you did this instead? What if every time I'll add it, I'll go ahead and give you a comparator. Every time I search for it, I'll give you a comparator. Every time I do something, I will give you a comparator. That could lead to inconsistencies. You could use a comparator that's in ascending order on one call, and then a comparator for in descending order on the second call. Right? And that'll totally screw up the tree, and it's not a binary search tree anymore. Right? So I'm going to provide it at instantiation right there. So this.cmp is equal to cmp. Okay. Over here, I think that what you can do is integer and then compare to. That's one way. Nope, that's not right. What would it be? Comparator dot natural order. There we go. There. Yeah, that's another way of doing it. It's not parameterized. Yeah, fine. I'll do it properly there. So what I would want to do is comparator for integers. CMP is equal to the natural order, and then hand that over. And now I don't think I'm going to get, oh, well, it's complaining that I don't have Lango Wrangle there. That's why. There we go. And now it's all happy. It was just giving me warnings before because it couldn't necessarily infer the type. Did you mean integers? Yes, I meant integers. I explicitly say it. Right? All right, we can test it by, say, bst.add 20, bst.add 30, bst.add 10. If I did it in that order into an initially empty tree, what would we expect? I'm going to add 20 as the new root. I'm going to add 30 as the right child because 30 is greater. I end up adding 10 as the left child. So it should look something like that, right? How do I do that? How do I verify that? System.out.println. Ooh. All I'm doing there is adding a line so that I can set a breakpoint. Okay. Then I'm going to go up to my debugger. Actually, let's make sure it works first because I'm pretty sure that it won't work. Let me go back to my Java perspective and get rid of this. No, I want by it. Sorry. Let's go ahead and just run it. Stop. Run the demo. Just straight up because I know that it's not going to work immediately. Previous is null. Right? What's going to happen there? When you try to add something, previous is null, current is the root. But with an empty tree, what is the root? Null. So does this while loop ever execute? Nope. So how can we make the new node be left or right child of nothing? We can't. Previous is going to end up being null, and that's why we get this null pointer exception right on 48. Okay? That's going to be one of those corner cases. If this dot size is equal to 0, in other words, it's empty, then we need to do something else exceptionally. Tree node t new node is equal to new tree node of elements of type T with X, this dot root is now equal to that new tree node. And in fact, let me just go ahead and do it in one liner here. There we go. I don't need to keep track of that. What else do I need to do? Sorry, let me go ahead and take this. I'm going to pause the, let's see, just a second here.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat. Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat. Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat. Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat. Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just
All right, there we go. All right, so where were we? We were adding something. We've got the new root node. This dot size is going to have to increase by 1. And then we return true because we had an effect on the tree. Okay. All right, so when we execute that, I think that that goes away. Foo is printed because it was just a dummy print there. But now that allows me to go into my debugger. And this is a nice way that you can actually verify that the actual structure that we expect right here was actually built, right? So the way that I'm going to do that is I'm going to examine, come on, where are my variables? All right, stop. Let's run it again. There we go. All right, now they appear. So there's my binary search tree, and of course there's no toString method, so I'm just getting a bunch of gobbledygook here. But if I expand it, I can look at the root element, right? And expand the root element and see that the element held there is 20, just like I expected over here. And then it has a left child and a right child. Its parent is null, which I expect. There's the left child, which is holding the element 10. There's the right child, which is holding the element 30. So there's the structure that I would expect, right? Now, that works for small things. You can verify it visually here. In fact, that's what a lot of you have done throughout the semester. In fact, you should put that in your design document write-up. When you run it against the grader and you look at the expected output, look at your output, right? That's visual inspection. That's visual verification. right? You're not, if you're running JUnit tests and more formal unit testing, great, that tells you pass, fail, pass, fail. But if you're doing something like looking at the toString method and seeing if it's well formatted, then that's going to be visual inspection. It passes my visual inspection. So it passes my visual inspection here, all right? All right, so let's go back to our Java list mode here. But, you know, it's okay for small ones. So what I like to do is I like to, you know, do at least, you know, something a little bit more, more rigorous, right? Not a full JUnit test, of course. You can see the JUnit tests in your lab this week. But what I want to do is I want to create some random numbers. Random R is equal to new random, right? And this is based on the time, so it'll be different every single time I run this. But I'm going to go ahead and put in 10 random integers here. For int I equals 0, I is less than 10, I plus plus, bst.add r.nextInt. I'm going to keep them small, between 0 and 100, or inclusive, exclusive there. So it'll be between 0 and 99 there, right? Now, when I do this, of course, I'm not going to be, I don't want to look at 10 different things. I don't want to, you know, traverse left or right or whatever. And so what I generally like to do is I like to use some visualization tool. I'm going to uncomment this at this point. Right? Oops, come on. There. No, no. Okay, fine. I'll do it one at a time. All right, there we go. All right. So does anybody use LaTeX? No, not for math or something like that, for your lab reports or something in electrical engineering? No? Okay, that's fine. If you ever get the chance to learn LaTeX, it's got a very, very high, you know, learning curve. But once you learn it, you want to use it for everything because it's beautiful, right? And one of the packages in LaTeX is this thing called TXI. It's a way that you can draw diagrams, okay? And it's, the user manual is like 1,000 pages long with examples. But in any case, what I'm going to do is, well, first of all, I have to break encapsulation here very briefly and make the root public, or at least package protected here. Because what I'm going to do is I'm going to hand off this binary search tree to this method, and it's going to produce a bunch of code, TXI code, to represent the tree visually. Right? So what was it? Tree utils.toTXI BST. Right? Let's run this. Now instead of printing out foo, it's going to print out this TXI picture stuff. Right? It's still just a bunch of code. Right? So now I'm going to go ahead and go to a website that is responsible, that you can use to, it's called Overleaf, overleaf.com. There we go. Right? Generally, if you're going to do LaTeX stuff, you got to install a LaTeX editor and a LaTeX compiler, basically. But Overleaf is an online web-based version of it where it compiles it on their servers and stuff, as long as it's not too slow. So let me go ahead and go into this demo here, and you can see that I've already done it at some point with another section, but let's go ahead and get rid of that. And I'm going to cut and paste that TXI code and recompile it to see what it looks like. Right? Come on. All right, it's having trouble there. Come on, what the heck? What's wrong with it? Okay, what's wrong with you? Begin, TXI. Oh, looks like I didn't cut and paste everything. It was missing a square bracket there, sorry. All right. And no, I didn't. Okay. Anyway, there we go. All right, so unfortunately we were really unlucky and got a skewed tree here because the first random number was 1. But look at it. I mean, is it a binary search tree? Yeah, look at 62. Is everything over here less than 62? Is everything over here greater than 62? Right? Visual inspection. I'm pretty convinced at this point that this is the correct tree. Right? Here's another test that I set up. Right? If I insert elements in the following order, 50, 40, 60, 20. Right? And let's go ahead and erase everything now. 50, 40, 60, 20, 45, 90, etc. In other words, top to bottom, left to right. What was that traversal called again? That was a breadth first search, right, using a queue. Right? If I insert them in that order, I should get this tree. Right? And that's what this does right here. It does it in that order, produces a tree, adds the result, and then returns a large binary search tree. let's go ahead and verify that that actually works. So BST is equal to tree utils dot large BST. And oops, what's wrong? Okay, I didn't save it, that's why. There. Let's run that again. Copy everything this time. And paste everything this time. And recompile it. And we got the exact same tree. All right. So I have 99.9% confidence at this point that those two methods work. Okay? That means that we can move on. But first of all, before we move on, let's consider some refactoring here. Remember that I cut and pasted a rather large chunk of code here. Right? There might be an argument here for moving that code to another function so that these two functions can use that same function. Right? In this case, though, I would argue against it, because you're doing something fundamentally different here. You're keeping track of only one node here, but here you're keeping track of both nodes. Right? Okay? So I would say that those are different enough that a copy pasta is warranted and okay. Right? But at the same time, we're probably going to be doing searching over and over and over again, because for deleting, to delete something, you got to find it first. So let's go ahead and take that code and generalize it. Right? Public tree node t find node t key. Right, there we go. All right, now instead of returning the element, what I'm going to do is I'm going to return the node. Right? Down here, if I of course don't find it, then I will return null. Up here now, this entire function can now be replaced with a this dot find node of key. Right? There we go. And then I can get rid of that code. Excuse me. Now, if current is equal to null, then I will return null. Else, return current dot get element. There. Now I'm not repeating myself. Right? And I've got this nice utility function, this convenience function, that allows me to find the tree node of any given key so that I can reuse it when I go to implement this delete method down here. Okay? Before we do that though, should this be public? Certainly search should be public because you need a way to interface with your tree, but should I allow the outside world, should I just allow anybody to grab this tree node? Probably not, because then they can go mucking with the internal workings of the tree. They can reset the parent, they can reset the left child, and violate the binary search tree property. This is what we called a leaky abstraction. Right? We don't want people to have access to our nodes in a linked list. We just want them to interact through the interface. So I'll make this private. Right, there we go. And of course, to-do documentation. That sets us up for the last one right here, delete. Right? Now remember that there were several cases. Each one of them, though, the first step is find it. Right? This dot find node of x. Right? That gives me the tree node to delete. I'll call it to delete. That's the one that I want to delete. Now, if you're trying to delete, say, 42, right? Well, you find it first, and you find that it doesn't exist. You get out null. What should we do then? We could throw an exception. We could return without doing anything, null, whatever, right? Or we could return a value here. If to delete is null, I will return null because nothing happened, right? Otherwise, eventually, return the element that is deleted. Right? That makes the most sense. Before I had this as a void function, right? But I want to delete that node element, and okay, it's out of the tree. Here you go. If you want to ignore it, that's your business. But we'll go ahead and give you that element that you just tried to delete. That's way more usable, right? As an interface. So eventually, we'll return the element that's to be deleted. We can do that by saying to delete dot get element and return it. Oh, and by the way, what should I do with the size while I'm at it? minus, minus, there. All right, now let's outline the rest of this because this is the most complicated one. Remember that we have three general cases here. If you have a leaf, if you have a left child or a right child but not the other, and then if you have both children. So, case 1, it is a leaf. Right? So if to delete is a leaf, then we'll do it that way. Right? Okay? Else if, and then we'll continue on later on here, case 2. Case 2, it has a left child, no right child. Case 2A and B, I guess we'll call them. It has a right child, no left child. And then case 3, both children. Okay? Let's take care of the simplest cases first here. Is a leaf. How do I determine if a node is a leaf? It has no left child and it has no right child. Seems to me that we designed it that way to begin with, though, with a convenience method like that, huh? Is leaf, right? So remember that, you know, if you just invest time in designing something up front, it'll pay you dividends later on, right? And this is an example of that. Dot is leaf, right? We foresaw that we would want to ask questions like, are you a leaf? Are you a left child? Do you have a left child? Et cetera, right? And so we put those into our node class, and now we can use them. If you are a leaf, then what do? We go to the parent and set its left or right child to null, right? Okay? So case 1A, if to delete is a left child of its parent, then delete, then set parent's left child to null. Right? Otherwise, case 1B, if to delete is the right child of its parent, then set the parent's right child to null. Okay? So how do I determine if it's a left child or right child? If to delete is a left child, that would be nice. Right? Well, if you didn't foresee that you'd want to ask that question and then you want to ask that question later on, then add that functionality. Right? Because this is a tree node thing, right? Who's responsible for answering that question? The binary search tree class? No. Good encapsulation says that that question should be answered here in the tree class, or in the tree node class. Right? So public Boolean is left child. Right? And then is right child as well. We'll need that. Right? How do I know if I am a left child? Right? I go to my parent and ask it, is your left child me? Right? So there's this famous poem, I guess, or riddle or something, that this guy walks up to a portrait on the wall and says, that's as good as my art gets, folks, and sees this portrait and he says, I know this person. Brothers and sisters I have none, but this man's father is my father's son. So this man in the picture here, his father, his parent, is my father's son. Who's the guy looking at? Himself. It's a portrait of himself. Right? So again, brothers and sisters I have none, but this man's father is my father's son. It's a self-reference. And that's what we're going to do over here. Right? If parent.get left child is equal to me, then I'm a left child. Right? Else return false. Okay? Now what should I be even checking before that? What is one node that doesn't have a parent that you can ask this question to? What's the one node here that has no parent? The root. So is the root a left child, or is the root a left child? If this is a root, then return false. I'm not a left child, I'm not a right child. And you want to take care of that separately because this would end up with a null pointer exception right here instead. Right? Let's clean up this code a little bit, because if you're going to do an expression and return true, and then otherwise return false, just return the expression. Return that. If it's true, it'll return true. If it's false, it'll return false. Right? If it was the other way around, you would just negate it. But otherwise, that's much cleaner code there. And it's much cleaner code that we can copy pasta and go with a right child. Right? If you are root, you're not a right child. Otherwise, if I go to my parent and I say, give me your right child, is that me? If so, then yes, I'm a right child. Right? All right. So if toDelete is a left child, then as we said, set the parent's left child to null. Right? This, or not this, but toDelete dot get parent dot set left child to null. Right? Do you see that chain right there? That's beautiful object-oriented programming code. That's a pattern. It's not exactly the pattern that I'm thinking of, but there's this pattern called the fluent pattern, where you can chain calls to a function, right? And it basically allows you to think in plain English here. toDelete's parent set its left child to null, right? That's exactly how I wrote it, and that's how exactly what the code looks like. Right? Else, case 1b, I don't know. I'll put them all both above there, right? toDelete dot get parent dot set right child to null. Right? Now you might, toDelete is about to be deleted, and you might, in other programming languages, you would also have to make its parent null, right? It's pointing, making a reference back to its parent. You'd have to sever that connection as well, right? Because there are actually two references here. There's a reference to its child, and then the thing that you're trying to get rid of is a reference back. It's kind of like a doubly linked list. We've severed one, but we have to sever the other two. In Java, though, we don't have to worry about that. Garbage collection will take care of it for us. Right? But if you were in C++, you would certainly have to do something like that. And then you'd have to delete the actual node and clean up the memory there. Right? Okay. I have not done the other three major cases here, but let's go ahead and test it. Right? I'm going to test this with my large binary search tree. BST dot delete. What could we delete over here? Well, I mean, we can't delete 50 yet because we haven't implemented that, but we could certainly delete, say, 12 and 95. Why did I focus on two of them? One is a left and one is a right. I want good code coverage. I want to make sure that both of those cases are valid. So I said 12 and 95. 95. And I want to make sure that it works. I'm going to use the same testing here, right? I'm just going to print it out after I have deleted those two things. Come over here and recompile this. So there it was before, our 12 and 95 now gone. Yay, it worked. Visually, right? Okay. All right. Back to the implementation over here. All right. Case 2a, it has a left child but no right child. Okay. Else if. You could do this, toDelete dot has left child and toDelete dot has right child, but negate that. Okay. There's my case 2. Let's go ahead and write the other case immediately here as well. Else if toDelete has no left child, but it has a right child, negation, and positive on that one. Right. There we go. Okay. What's case 3? Else, do I need an if here at all? There's only 4 possibilities, right? Because there are 2 children. Each one is either there or not. So else. This is simply just an else down here. Okay? Reformat everything. It has a left child, no right child. All right. So let's go over here and look at an example. It has a left child, but no right child. So for example, here, 49. We want to delete 49. What are we going to do? We're going to take 48 and promote it up. That means making 45 its right child point to 48, making 48 its parent points back to the parent of 49. Okay? But is that the only case? What if it was different? What if it was something like this? 45, we'll go with, get rid of all this. What if it was 45, okay, 45, and it had a left child of 43, and that child had a right child of 44. And I wanted to end up deleting 45 right there. It would, in the first case here, we would say, oh no, we need to make its parent's right child point to this new node here. Right? Here we're saying, no, we need to make its parent's, maybe I've confused myself here. Anyway, it would be, okay, let's go ahead and dot this to, I've already used 50, 49.5, there we go. That'll work, right? So if it was one or the other, basically what I need to do is I need to say, 45, you now need to point to the right child, or you need to point to the left child, okay? There's actually going to be 4 cases here, okay? 4 cases between these two. So it has a left child, but no right child. So that means that we need to set to deletes parents left or right child to deletes left child. There we go. Right? Correct, I should say, not right. So it has a left child, no right child. It has a left child, no right child. So that's this case right here. We're trying to delete 49 right now. Okay? So we make the parent's right child point to 48. If to delete is a right, so case, I don't know, case 2a I, dot I, there we go. If to delete is a left child, case 2a dot I, if to delete is a right child, We need to take care of both of those 2 cases, right? So what do we have here? To delete is a left child, right? That's actually not our case here. This is our case. To delete is a right child, right? Because 49 is a right child of 45. Now let's describe this. To delete's left child's parent now needs to be set to the parent. So to delete dot parent dot get parent dot set right child, right? To delete dot get left child, right? And then I need to set the parent of the left child, so to delete dot get left child dot set parent to delete dot get parent. All right? And this is an else condition here. Come on. I should have been outlining the conditions first, sorry. If some condition here, and I'll bring this down here. There. If, else, and then move this down there and indent all that. All right. I'm pretty confident in this one because that's exactly what we're visually describing right here. Okay? What is my condition here though? If to delete is a left child, so to delete dot is left child, that would be really nice. In fact, we put it. Yeah, are you a left child? Yes, right? And so if it's otherwise it's a right child, right? So what do we do in this case here? That would be the other case. So let's go ahead and write it out actually. Let's get rid of that. And I still want to delete 49, but it had a right child called 49.5. There we go. All right, now outline that. I get the right child, and I set its parent to the right child of 45. So to delete dot get parent, I get its parent, and I set right child to delete dot get right child. Get right child. There we go. And now what about the right child? I get the right child of to delete, and I set its parent to the parent of to delete. Right, get right child. There. All right. So we've got half of the cases down now. Right? Everything is just going to be symmetric down here, except that wherever you put it had a left child, you change the left child to a right child, basically. Right? So let me go ahead and grab all of this, right, and copy it there. All right, so there is no left child, but there is a right child. Let's look for a situation that we can do over here visually to get ourselves straight on this. 60? Would that be right? I want to delete, no, let's delete, it has it does not have a left child, but it has a right child. There, yeah, 60 would work, right? Because it has no left child, but it has a right child, okay? So we want to delete 60 here, and it has it is a right child, and so this is our case right now. I get the parent, and I set its right child to the right child. There we go. And then I get the right child and set its parent to the parent. Okay? Now, let's suppose that nothing is over here. Let's see. Go ahead and sever that connection entirely. And suppose that it had a left child here of 45. There we go. So it is a right child, and so I get the parent and set its right child to the left child. Get the parent, set its right child to the left child. Then I get the left child and set its parent to the parent. Now, I'm crossing my fingers here and hoping that it works, but of course, we're going to end up testing it rigorously here. All right? So the ones that we just worked on were 49, and then way across on the other side of the tree, 60. Right? Let's see if that actually works. There's our original tree, and I'm trying to delete 49 and 60. Let me highlight those so that we remember them. 49 and 60. Okay. So what should it look like after? Well, let's just go ahead and run it. And take a look at the visualization over here. And then compare them. So 49 is gone and 48 is its new right child. Right? That's what I expect. 60 is gone and 90 should be the new child with everything else hanging off of it still, 80, 75, 85, 95. Now I'm not done yet because there were 4 cases that I just outlined, but I've only tested 2 of them. Right? So if I were going to do this formally, I would have to make sure that I'm doing the other 2 as well. Right? And in fact, I would know how to do that because if I did this formally in a JUnit test, remember that code coverage tool up here? Right? It would have ended up highlighting all 4 of these cases if I had all 4 of these cases. Otherwise, it would not end up highlighting this as not being tested. That's when I go in and make sure that I have a test case that's exactly that thing. Right? All right, I think we can get this last one done here today. Okay, both the children are there. Right? So, step 1, find the maximum in the left subtree. Right? If we don't get, at least let's do this part, and then we can finish it up on Thursday. Right? Okay. So, how do I find the maximum in the left subtree? Let's come over here and once again de-highlight everything. All right. Think about the entire tree. How do I find the maximum in the entire tree? Keep going right until you can go right no further. How do I find the minimum? Keep going left, 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 left until you can go no further. Right? If I wanted to do it for a subtree right here, I would just do the exact same thing, but I would start at that node instead. So let's give ourselves all of those convenience methods. Public, T, get min. Right? Public, tree node, T, get min. Right? Or sorry, get min. Right? Starting at a tree node, T. Start, I'll call it. Right, there we go. I want both of those. Why? Because I want you to give me the tree node so that I can actually get the element. But I also want you to be able to start at an arbitrary node because I'm going to go left, and that's where I want to start. Up here, for example, in this third case here, what I'm going to do is I'm going to say toDelete.get left child, and I want to get the maximum out of that. This dot get max. Right? That's where I want to start. I don't want to start at the root. Right? And so this is tree node T, what max of left, I'll call it for now. Right, there we go. I guess I'm doing min. So let's go ahead and copy paste this and do it for max as well. There. Now it's happy up there, but of course we have to do this. Let's do the most general one here first, where we start at an arbitrary node and keep going left, keep going left, keep going left until you can get no further. So tree node, T, is going to be very, very similar to what we've done before, and as well as the linked list. You have a current, right? And that's going to be equal, current is equal to the start, wherever you're going to start. Keep going left. While current, here's my first attempt, is not equal to null, then current is equal to current dot get left. Just keep going left, and keep going left until you can get no further and then return current. Careful, just like our problem with previous and next, we jumped out of this while loop. How? By current being null. Is that going to help anybody to give you null? Nope. So my criteria here should change. While the current has a left to go to, right? Dot has left child, then go to it. That allows me to stop short, right? While you have a left to go to, keep going left. Stop on that leftmost node and then return it. That makes this one really easy, right? This dot get min of this dot root. And just return that element dot get element. Now you do have to be careful here. Corner case, what? Is there a minimum in an empty tree? So if there's a tree is empty, what should I return? Null. Right. Otherwise, then go ahead and try to get this or whatever. Right. Same thing down here, but instead of calling that, I would go max. There we go. How would I do the max? Copy pasta this and change it how? Oops. You don't go left, you go as right child. Child. Get right child. There you go. All right. Let's test that really quick. I'm not going to delete anything anymore. Instead, I'm going to say BST, after all this stuff here, BST.get min and BST.get max. Let's print those out. So sys copy, paste, BST. There we go. And copy, paste. What was the min? What was the max? 2 and 95. Let's see if it works. 2 and 95. Right. All right. So, yeah. I mean, how much more do you want to do today versus Thursday? We can finish this up on Thursday if you want to. We've got the maximum of left. Let's at least outline this so that we remember it next time. What are we going to do? Right. If it has both children, go to the left tree and find the max value. Promote that to the deleted value. Then delete the promoted node. Right? It's guaranteed to only have at most one child. Actually, I think we can do that in a couple of lines. So to delete dot set element to max of left dot get element. Right? That's all there is to it. All we need to do is now make sure that that set element is an actual method. Remember when we, let's do where's the tree node? Right? We initially made this final, and you want to make things immutable unless you have a very good reason to not do so. And now I have a very good reason not to do so, because I want to change it. Right? So, public void set element, oops, set element, we're not C# here. C#, the style in C#, the Windows way is to all your methods are upper camel cased. Right? So I can tell when somebody's had to come from a C# Microsofty background by their naming convention. Right? T element. Right? So this dot element is equal to element. That did it, didn't it? All we did was promote it to the top. And now what's the last thing? Delete the promoted node. I have the promoted node, don't I? And I have a method that will delete it, don't I? Delete. This dot delete. What? Max of left dot get element. Careful. Once I've deleted it, say that I want to delete 40 here. It has both of its children. I end up putting 40 up here. Between these two lines of code right here, there are two 40s right now. Right? What will this end up deleting? This one right here. That's the one that I don't want to delete. I want to delete this one right here. Okay? So, what if we just switch these around? I have the tree node and its element, right? Just go ahead and delete that other one, and then promote the node, right? Right? What'll that do? That'll end up deleting 40, and I've saved 40 off over here to the side. This will end up deleting 40, the only 40 that's in there. Remember, we don't allow duplicates. And then we erase this value and put 50 there. That'll work. And remember, it'll work because, actually, will that work? Yeah, because we're not deleting 40 here. If we end up deleting 50, then we're ended up deleting 49. That's what gets promoted up here. I don't know why I was saying that 40 would get promoted up. That was weird. Sorry. But anyway, it will work here. Right? And maybe make sure to decrement your size and do this. Let's just go ahead and try it on a couple of examples over here before we quit. And let's go ahead and go to BST.delete. Let's go ahead and delete 40, 20, and 50 in that sequence. 40, and then print it out. And what did I say, 20? And then 50. And I'll print it out 3 times here, and we can see the progression, right, when we run this. Come over here. We can have more than one figure. Recompile it. So remember, there's the original, and we're going to delete 40, then 20, then 50. That's kind of small. There we go. All right, delete 40. What's going to end up happening? You go to the left subtree and you promote 28, which is a which is a leaf, and it's therefore gone. 28's there. Right? On the next iteration, on the next test, we delete 20 right there. So we go down to the left subtree, get the maximum, which is 15. So 15 should be up there, and then 12 should now be up there. Hey, cool. We're about to delete 50. Right? What happens is we go to the left subtree, promote up 49, and then 48 becomes the new leaf node there, and it works. Right? So give this as much of a workout as you want. Right? The takeaway here, though, is that everything is going to be order D. order D, order D. The problem is, of course, we don't have a guarantee on D, right? It could be an entire skewed tree. What we'll do on Thursday is our last data structure, where we do have that guarantee. It's called a heap, or a min heap, right? And that's where we'll pick it up on Thursday then, right? So I will transition out here.